Hey, it's Mr. Saltano. This video is going to be talking about half-life. So, if you recall, we talked about how a radioactive element is one in which the nucleus is unstable, right? So if we have radioactive decay is happening, where you have those dangerous radioactive materials, because of an unstable nucleus. Now we said you could either have too many protons or too many neutrons, but in some way the nucleus is unstable because of that. So here we have some alpha decay happening, right, where you have an unstable uranium nucleus and it's emitting alpha particles. So that's just one of the types of decay. So this is all going to be related to what we're talking about in this video as well. So for now, we know that this is undergoing alpha decay. What half-life is half-life is the amount of time, so half-life is always a time period. It's the amount of time it takes for half of the radioactive material to undergo this decay. So in other words, if you had 100 of these radioactive nuclei, half-life would be how long it took for randomly half of them to undergo this exact process that you're looking at here. Or it could be beta decay, any type of nuclear decay. But half-life is the time period that it takes for half of them. Let's say we had 100 atoms. It's the time it takes for half of them, 50 of them, to do this process. It's a useful measure of time for various reasons that we'll get to in a moment. So for now, you want to think of this purple sphere as our radioactive uranium-238, like the beginning of the process. And then you want to think of this red sphere that it changed into as the thorium that it changed into after it did the radioactive decay. Okay, so that's going to be useful for our next simulation. So purple is the original radioactive uranium, and red is the new one. Is what it became afterwards. Okay, so like I said, we are looking at half-life, right? And in this sample, we're starting with 64 radioactive elements. They're all the same element. Let's say that they're all that uranium we just looked at. There's 64 atoms of that in this sample. And in this case, our half-life, which is always a time period, right, is 1 year. So we've got our original radioactive sample. Let's start the clock. So time is passing. And as time passes, once we get eventually to the 1 year mark, notice that half of these atoms have undergone decay. That's why we call it the half-life, because it's the amount of time it takes for half of the radioactive material to undergo decay, or to transform into another element, essentially, because of that radioactivity, because of the unstable nucleus. So now we actually have 32 particles left. So there's actually 32 purple, 32 particles that are still radioactive, essentially, after the 1 year mark, because the half-life is 1 year. For now, let's just focus on what's happening up here, and we'll look at the bottom table later. Okay, so now more time is passing, right? And eventually we get to that point, more time is passing, you get to that point where another year has passed. So in other words, a second half-life has passed. 2 half-lives have passed because each half-life is equivalent to 1 year. Over the course of that happening, if we look back really quick, we see that another half of the sample, half of the purple again, has actually undergone nuclear decay over the course of another year. And so now there's actually only 16 purple left. So every half-life, another half of the remaining sample will undergo nuclear decay. So it's not like half of the sample decays, and then after another half-life, the rest of it decays, the second half. That's not how it works. It's half of the radioactive material. After that first half goes away, then you're left with half of it, right? And then what happens is half of the half will decay, and the process will continue like that. Notice how, as well, some of these simulations show these particles disappearing, but they're not disappearing, they're just transforming. So that's a really important point. During half-life, or during time that this nuclear decay is happening, it's not like atoms just magically disappear. They're actually just transforming into a more stable nucleus as a result of that decay happening. That's why decay happens. Alright, but let's let more time pass. And then so maybe we'll see another half-life occur, another year occurs. And as that time is passing, notice more of the purple turns to red, more of it transforms. And as a result, now we only have 8 particles left that are radioactive. 8 atoms that are still radioactive. So we took another half off of our previous sample that was 16 that were still radioactive. Now you could probably guess what's going to happen after another more time passes, another year passes, and then gradually half of our remaining radioactive material at random also transforms. So now, after 4 years, 4 half-lives, we only have 4 radioactive particles left, and we began with 64. Each half-life that happens, we halved how much we had left over. So we've got only 4 particles left. Can you guess, after one more year, one more half-life, how many particles will still be radioactive? So we'll start our timer going. Another year. And now, after 5 years, we only have 2 radioactive particles left. Okay, and then we'll go through, one more year is happening. You'd probably guess again how many particles will be radioactive after one more year. Now we can see that that's only 1 particle left after 6 years, after 6 half-lives. So that's the process that's happening essentially, is after every half-life time period, which is different for every element. It's not always 1 year. Chose 1 year just to be simple. After 1 year, exactly half the radioactive material will transform into something new. And then half of that, leftover half, after another year will continue, etc., etc. Okay, so now that we had a chance to see the general process, now let's kind of rewind and focus on this table at the bottom. So we'll rewind time a little bit. Alright, so if we're starting back at the beginning, after no half-lives have passed, and we still have all of the sample, right? The fraction of it that's still radioactive is 1 over 1, or just 1. 100% of it is still radioactive. So let's see the time passed again. After our 1 year, we're left with half of the remaining sample. So now we're focusing on this bottom table. This is true no matter what sample you're looking at. So the top part was kind of specific to this sample because the half-life happened to be 1 year, which isn't always the case. And we happen to begin with 64 particles. No matter what, though, this bottom table will be true. This will be applicable to all samples. So regardless of how much you began with, the fraction that's left after 1 half-life is half, which is the idea of half-life, right? That's how long it takes for half of it to decay. Okay, so we continue on, more time passes. After 2 half-lives, 2 years, because each half-life is 1 year, we end up having a quarter of the remaining of what remains is still radioactive. So we started with 64 in this case. Right now we only have 16 that are still radioactive, so that's a quarter of the original sample. Now after 3 half-lives, and this will always be true, we have only 1/8 of the sample is still radioactive from the original. And then after 4 half-lives, so 4 years in this case, we have only 1/16, and you can probably see where this pattern is going, kind of race through. Now 1/32 is still radioactive, and then finally 1/64 is still radioactive. So no matter how much sample you start with, this will always be true. Where after 1 half-life, there's half left. After 2 half-lives, you take a half of a half, which is 1/4. After 3 half-lives, you take 1/2 of the 1/4 that was remaining, and the pattern continues like that. So that's how half-life works with this bottom table, no matter what your sample is. Here's sort of seeing it again. In this case, it's kind of the opposite. Starting with radioactive red. This half-life is 0.16 seconds. Some half-lives are extremely fast. So after 0.16 seconds, half of the sample has turned blue. After another 0.16 seconds, half of the remaining red has turned blue, right? So 2 of the 4. And after another 0.16 seconds, half of the remaining 2 red has transformed. So in this case, the red is polonium, radioactive isotope, and it's forming lead, which is more stable. So it could be, there's all kinds of different radioisotopes out there that undergo half-life as they're transforming to more stable nuclei. So here's another really good use for this. You may have heard of carbon dating. This is what we use for fossils in order to determine how old they are. So not to get into all the details, but there's a certain isotope, carbon-14, that is present, and there's a whole lot of it present when the species first dies. The half-life of carbon-14 is 5,730 years. So after 5,730 years, we would expect half of the carbon-14 to still be there. Half of it will have undergone decay. The other half will still be radioactive. After 11,460 years, 25% of the carbon-14 that was supposed to be there will be there. And so, kind of in summary, if we check how much carbon-14 is left versus how much we would expect to be there, we can use its half-life to figure out exactly how old the fossil is. So carbon-14 is a great way to determine how old fossils are. Another really important use, technetium-99 is a radioactive element with a half-life of 6 hours. It's used as a tracer in the human body. So it's used in all kinds of different imaging things, like if you want to sort of image the brain or look at bones. It's really useful because it is radioactive, so while it's in the body, it is sending out radioactive signals that can be picked up by a machine scanner, right? So that decay can actually be picked up by a machine scanner. But they also pick that particular isotope because it has a half-life of only 6 hours. So over the course of a day, a 24-hour period, that's going to be 6 hours times 4, right? So in other words, 4 half-lives will have occurred. So after one half-life, half the sample's gone. 2 half-lives, a quarter of the sample is still there. After 3, an eighth of the sample. And after 4 half-lives, a 24-hour period, if each half-life is 6 hours, only 1/16 of the radioactive material is still in your body. So extremely useful for that, and that's the reason why we use it for that, essentially. The last thing is, half-life is also necessary because nuclear waste takes a long time to break down, right? We're using nuclear waste in our power plants and things like that, and we need to track the half-life so we know when it's safe to be around the material again. Some of it takes thousands of years just to become not radioactive anymore. Or even places like Chernobyl, which is pictured here, trying to figure out when we can go back or when it's safe to be around there. You have to use the half-life in order to be aware of that, to know how long it'll take for the sample to finish decaying eventually and be stable again. So that's it for half-life. Thanks for watching. Remember, chemistry is everywhere.